So are there any homework questions? Three point three. Oh, 14. It says, this is from 3.3, but find the derivative of the following function by first expanding or simplifying the expression. Now, even if they didn't say to simplify this function first, once we got into 3.5, we had the quotient rule. And so we would look at that and probably be inclined to use the quotient rule on that, which you totally can. It's just going to be a lot more difficult than to simplify first. So if we simplify the function first, divide each thing by e to the w, then you have something simpler to deal with, which inherently means a simpler derivative process. So this is still g of w. This is just going to be 5. We've got 6e to the 2w over e to the w, which would give us what?
6e to the w.
Yeah, just 6e to the w. So that's g of w. So much more simple of a function to take the derivative of, because now we don't even really need we just need basically two rules over a sum and the derivative of e to the w instead of a quotient rule. So then g prime will be 6e to the w plus 0. It's the same result you would get if you used the quotient rule, factored stuff out, simplified. So, I always look for like simplification of functions. I don't know that it's common in every problem, but definitely when you can simplify. When we get into the section 3.9 and start looking at exponentials and logarithms, there's some properties you can utilize to make things a little bit simpler as well. Okay, does that all make sense? Anyone have questions on that? Okay. Any other questions on the homework?
I guess it's not really a question for the homework, but in 3.7 there's one question that's like 3 chains and then a product or whatever. I was just curious if you would be having us do stuff, and the final thing ends up having like 4 or 5 terms on it. So I was just wondering if we would be doing something like that on the exam, or if it's going to end up being like that long, the string.
Yeah, so on the exam, at most there would be like 3 chain rules, but like a chain rule and then a product rule, another chain rule, another chain rule, no. When we get into 3.9, we'll look at sort of like those kinds of functions with many derivative rules present. There's a process that we look at in 3.9 that can simplify taking derivatives like that. But yeah, on the exam, no, I would just have like 3 chain rules maybe for one question, not like 3 chain rules with a product rule with a quotient rule, nothing that involved. Yeah.
Going back again to 3.2, question 16.
Yeah, so a little forgotten, 16 over 2.
So it says a line that's perpendicular to another line or to a tangent line is called a normal line. Find the equation of the line perpendicular to the line that is tangent to the following curve at the given point. So find an equation perpendicular to the line that is tangent to the curve at the given point. So that's just kind of a separate problem. That's finding the equation of the tangent line to the given function at the given point. And then once we've done that, this second part here says find the equation of the line that's perpendicular. And so the equation that's perpendicular at this point, we want -1. So the equation of the tangent line, we first have to find the derivative of 11x minus 12, which is 11. And then that is the slope of the tangent line we're plugging into our point slope formula. So we have y minus the y coordinate equals to our slope of the tangent line times x minus the x coordinate. So what do we get? Y is 11x minus 11 minus 12. Does that make sense? So what's I guess kind of weird about it, maybe not when you think about it, but the equation of the tangent line to our function, which our function was just a linear equation, right? So if you have any line, what's the equation of the tangent line? It's just the line itself, right? So we get the line itself in return. But then it says now that we have the equation of the tangent line, we want to find the equation of the line that's perpendicular to the tangent line. So our normal line is perpendicular to the tangent line. Lines that are perpendicular, what's true about their slopes?
Opposite reciprocal.
Yeah, the negative reciprocal of one another. So that's kind of what you have to remember here. How do we want to say that? So like if the slope of the first line is the negative reciprocal of the second line, then the lines with these two slopes are perpendicular. So all we've got to do is take the slope here, make it negative, and divide 1 by that. So the slope of the normal line has slope of -1 over 11. And then we just put that back into point slope. Again, the point we're saying find the normal line with this slope at this point. So we just have another point slope formula for that. Does that make sense? Yeah, so that's a 1 as well. I'll just erase this here just so there's, I guess, they're different slopes, but that's perpendicular. So finish that up. Does that make sense? Anyone have any questions about that? You do a lot more with normal lines and normal planes if you go on to Calc 3. So it's, and I think this example in our homework is about the only occurrence of a normal line that we see. But, you know, we know it is a thing. We have an example. They're out there. They exist. Okay. Did you have a homework question?
Yeah, I had a number 18 from 3.7.
3.7.
And the reason why is because when I did take the derivative, there was an x plus 1 in parentheses at the end, but I didn't really know why it belonged there.
Okay. So this was 3.7. Okay, so we have the function 3, e to the 3x times 3x plus 4 to the 8. So we're going to use what rule to compute the derivative of y? Ultimately, yeah. Ultimately, we would need a chain rule. But the function y itself consists of, you don't want to sort of look at those like other operations built in. Like the overall structure of the function y is one function of x times another function of x. So you have the product rule to take this function's derivative. This is a product of two functions. So we have the first times the derivative of the second. I'm just going to write this out. Times the derivative of the second, which is 3x plus 4, quantity raised to the 8th. The first derivative of the second plus the second times the derivative of the first. Second times the derivative of the first. So you've got to be able to recognize the structure of the function. If you started off by applying a chain rule, I guess depending on how you applied it, but if you just started off with a chain rule, your answer is probably not going to be correct. It's a product, we apply the product rule. Additional derivatives we can then compute off to the side, because that's the derivative of that function. We just need to find these derivatives. Oops. Okay, so we'll compute the derivative of 3x plus 4 plus 4 to the 8th. So now when we're addressing this derivative here, that's when we're going to think about the chain rule. So we have the derivative of the outer function, leaving the inner function alone. Then what?
Times the derivative of the inner function.
Times the derivative of the inner function. So this is our chain rule. Times the derivative of 3x plus 4. Which of course this derivative here is 3. So we'll just multiply that 3 with this 8 right here. So we know, again, we know if we're writing the derivatives out, like I would recommend you write them out, you know you're done because there's no derivatives left, right? That's the derivative of our second. So just put that here. We have plus this thing again. what's the derivative of e to the 3x?
3e to the 3x.
3e to the 3x, right? That's, I mean, it's a chain rule, I guess, technically it's a chain rule, but we said last class, maybe, I think, the derivative of e to a functional power is e to that power times the derivative of the power, which is just 3. So we can Okay, so then we're going to put that in for the derivative over here. And so I'm assuming that it didn't like that.
Yeah, didn't.
Okay, so from here then, what we want to do is you've got two terms involved with your derivative. Both terms, we want to look for the greatest common factor. So we have an e to the 3x that we could take out. We're going to factor that out. And both of them have a 3x plus 4 to the 7th power. So we're going to take that out. And then when we factor that out, we have 1 here, we have 24 here. Plus, we have one of these left over. Moves to the 4th. I'm sorry, plus 4 to the 8th. That's 3x plus 4 to the 1st. What about the e to the x's? We took out that e to the 3x. So we just have 3 there. So factor out greatest common factor, and that's what we're left with. Okay.
Could you factor out 3e to the 3x?
Yeah, now that we see it, right, the 3 and the 24, we could have factored out a 3 as well, right, from these two. Factor out a 3. Yeah. So that'll just be 1 there, and that'll be 8 there.
Then you just add common factors, right?
Yeah, then you just combine what's in brackets. But if you might have seen something different there, Luke, I'm not sure.
It was a little weird, but I think that's still the right answer. It may have just looked a little different.
Okay. We have 3x plus 12. We'll just write that like this, 3x plus 12. This is still all multiplied together. So I mean, and that's simpler because you've got a bunch of things multiplying together instead of a couple of things multiplied plus another couple of things multiplied. What we have simplified here in red is a lot easier when you have to start solving these derivatives. Like when is this first derivative equal to 0? This simplified version that we have here is a lot easier to solve than what we had originally. And that's usually the process, like when you have this really funky looking derivative with multiple terms, 95% of the time, the process is to factor out the greatest common factor, and then you have two things multiplying, which you can then set each one of those equal to 0. So greatest common factor is super, super common when simplifying derivatives. Okay. Does anyone have questions on that?
Thank you.
You're welcome.
I have another homework question.
Okay, sure.
It's 3.3, question 20.
So we'll get this in here first. All right, so we're given this graph, and we're given that capital G is 7 times f minus g. Is that 3, number 20?
Yeah.
Okay. So, you know, basically what they're giving you is they've got a little sloppy with their notation, but it's g of x is 7 times f of x minus lowercase g of x. We have the graph of f and g provided, and we want to find g prime of 2. So then in order to find g prime of 2, we first need to figure out what g prime is. So capital G prime is equal to what?
It would be 7f prime minus g prime x.
Okay, good, yeah. So 7 times a function of x, the constant doesn't get affected by the derivative. What's the derivative of f? We're just going to call it f prime. Minus the derivative of g, which is g prime. Does that make sense? It's a little more abstract because we don't have f and g, so we just have to label as f prime g prime. And then so capital G prime evaluated at 2 is 7 times f prime of 2 minus g prime of 2, lowercase g prime of 2. That's right here. So when we look at f prime and g prime, what is f prime of 2 measuring? How do we get that value?
The slope at that point.
Right, it's the slope. Remember, the derivative is the slope of a curve at some given point, right? So fortunately, they're linear. We don't have to guess what their slopes are at a particular point. We can say, all right, well, where's f? It's this blue one here. So at 2, we want to know what's the slope of that line at that point. That is the derivative. So what's the slope of the blue line there at that point?
-2.
Looks like we go 1, 2, 3, 4. Yeah, so that we've got a 1-to-1 ratio here with these grids. So we're going down 2 and over 1, -2. So the slope of that line, just put it here, the slope of this line is f prime. So that's just -2. Same thing with g. What's the slope at 2 here? What's the slope of the line on g? Yeah, so just count 1 over 1. The slope here is g prime. Does that make sense? So it's a little more abstract, but it's tying in a bunch of concepts, a couple of derivative rules, and it also has you remember, like, when I say the derivative at 2 is equal to 5, what does that actually mean? That's the slope of the curve when x is equal to 2. So we have -14 minus 1. That's what g prime of 2 is. Any questions on that?
Any other homework questions? So we left off, we finished this example, found the equation of the tangent line on this curve at the point 1, 1. Finished that last time. Okay, so I think a couple more examples here from, maybe 2 more.
But when you're finding the second derivative with respect to x implicitly, I guess we'll point out as we go along, but basically you want the second derivative to be another function of x and y. You don't want your second derivative to be a function of x and y prime. You wouldn't want your third derivative to be in terms of any of the derivatives themselves. So all derivatives implicitly need to be in terms of x and y. And so we can look back at the first or second page when we found that y prime for our unit circle was negative x over y, I believe. Negative x over y. So then we want to find the second derivative of our unit circle. So y double prime, we're going to take the derivative, second derivative by doing what? The derivative of y prime, right, which we'll find by doing quotient rule. Yeah, quotient rule. So we have the bottom times the derivative of the top. What's the derivative of negative x? Negative 1. So I'll just write that there. Bottom times the derivative of the top minus the top times the derivative of the bottom. What's the derivative of the bottom?
Y times y prime.
Y times y prime? So what would be, remember y is a function of x. What would we say the derivative of f of x is if we don't know f of x? F prime, right? So it's, yeah, we should just have y prime. Derivative of y is y prime. Okay, so there's the bottom times derivative of the top minus the top times the derivative of the bottom. And then we have to divide all of that by the bottom squared. So let's just call this minus, we'll just call that plus. So we don't want the first derivative there. We want the second derivative in terms of x and y only. So we're going to rewrite the first derivative was simply negative x over y. So we're going to rewrite that and see what we're dealing with. So we have our negative y plus x times the first derivative, which was negative x over y. And we have all of this over y squared. So there we have our second derivative. It's now only in terms of x and y, but we could simplify that a little bit.
When did the negative y minus, because we have negative y minus.
Yeah. Minus y minus a minus xy.
Oh, yeah, there it is. Okay, cool.
Yeah.
Yeah, I just.
So we just turn that to plus. This one here. All right, so we want to do a few more steps here to fix this because we've got a complex fraction, right? We've got a smaller fraction within a larger fraction. So how do we simplify these things like this? We saw it with limits a lot. So I'm going to multiply the top and the bottom of my fraction, numerator, denominator by
Why?
y, right? Because I have this smaller y in the denominator of this fraction here, so I want these two things to cancel each other out. So I got to multiply the numerator by y, which means I multiply the denominator by y. So again, not changing the value, not changing the function, I'm just changing the way it looks. Distribute the y into the top. The numerator, we have negative y times y, which is negative y squared. Again, this y out here and this y here divide away. We just have a negative x times x. I guess we'll write that as negative x squared. And then all of that's over y cubed. That's our second derivative, yeah.
Is it a rule that the first derivative of y is negative x over y?
Yeah.
Is that just a...
Yeah, we found that to be true.
Okay,
Yeah,
got it.
so we just resubstituted that.
Thanks.
It's negative x.
So can we simplify any more?
Yes.
Yeah, what if we factored out a negative 1 from the top? We'd have y squared plus x squared all over y cubed. What do we know y squared plus x squared is? 1, right? That's the original function we started with, or the original equation we started with. The unit circle says x squared plus y squared is equal to 1. So that's equal to 1. That's what we started with. So our second derivative is negative 1 over y cubed. So generally when you find, like I said, when you find the second, third, fourth derivatives implicitly, you have to look back at your prior derivatives to simplify that. And oftentimes your original equation, like we did here, you have to utilize that to like fully simplify it. So does anyone have questions about that? All right, look at one more example with the sine of 2y squared minus 8x equals 5 e to the y. So this, like I said, the notion of implicit differentiation shows up in 311 when we deal with related rates, where time is our variable. So you can relate like two spatial dimensions, you know, like horizontal and vertical, with respect to time, by using implicit differentiation. And a derivative that we see in 3.9 and in 3.10, many of those derivatives are proven or justified using implicit differentiation as well. So we're going to take the derivative of both sides of our equation. What's the derivative of sine of 2y squared? And we'll come down here and do this. There's the derivative with respect to x. Sine of 2y, y squared. So just remember that y sitting there is a function of x. It's an unknown function of x. So what rule are we gonna use to take this derivative? Chain rule, right? So the chain rule says we take the derivative of the outside, leaving the inside function alone. So what's the derivative of sine? Cosine. So there's the derivative of the outer. Cosine evaluated at 2y squared times the derivative of the inner. So we have this cosine of the quantity 2y squared. What's the derivative of 2y squared?
4y.
4y? What's 2 times the derivative of a function of x that's squared? So we take the derivative, ignore that 2, it's just a constant. We take the derivative of the outer function, leave the inner function alone, and then we multiply by the derivative of the inner function. So it should be the derivative of 2y squared should be 4y times y prime. Yeah. 4y, y prime. So like if we wanted to condense implicit differentiation and like oversimplify it, I guess, what we would say is anytime you take the derivative that has a y involved, you take it normally like you would with x, and then you just end up multiplying it by a y prime. So there's the derivative of sine of 2y squared. Minus the derivative of 8x equals to the derivative of 5e to the y. So what's the derivative of 5e to the y with respect to x? If you need to think about it as f of x instead of y, then please feel free to write that in. It's not gonna matter what you call y. So the derivative would be what?
It would be 5y e to the y prime.
Close.
Am I missing another y?
Yeah, you've kind of like missed.
Oh, so it's
Yeah.
so it's 5y prime
Yeah,
e to the y.
right.
Okay.
Right. What's the derivative of e to any function of f? It's still e to that function times the derivative of the function, right? And then we still have this 5 hanging out front. So there's your 5 times your y, e to the y rather, times y prime. So 5y prime e to the y. All right. Does anyone have questions?
Are you just taking the derivative of all the variables before you start actually putting them all together?
Yeah, yeah. So we take the derivative of the equation. We were asked to find y prime, so once we have the derivative of all of our terms or both sides of the equation, and then we can solve for y prime. So
So we want the terms with y prime on one side together, the other term on, or the other terms on the other side. So we have two terms in blue and purple that both involve a y prime. We need those on the same side. So it doesn't matter what side you put it on. If someone decides to put it on the right versus the left, your answers will be the same, but they'll just be off. They'll be off by a negative. Not that they're off by a negative, they just look differently. So let's just say we have, on this side, we have our cosine of the quantity 2y squared times 4y prime. And we're subtracting 5y prime e to the y, which means we need to put the 8 on the other side. From here then, we would factor out our y prime, because both of these terms have a y prime in common. We're left over with cosine of 2y squared times 4y minus 5 e to the y. Still all equals 8. So isolate y prime, factor out y prime, divide through by what's remaining. So our first derivative then would be 8 over all that stuff. You know, we might put the 4y out front just so we're not, usually that's just how it's written, just so it's not, there's no question as to whether or not what we're taking the cosine of. So we'll put the 4y in front of the cosine of 2y squared. But it doesn't really matter, as long as you know it's those two things are multiplied, we're not taking the cosine of that. All right, does anyone have questions on that? All right, so I really didn't have much in the way of notes already pre-made for 3.9. We're just going to sort of write these things out as we go along. The definition for the derivatives for the exponentials and the logarithms. We have we have e to the x as the only exponential we've looked at. So here we're going to get the other exponentials and all of the logarithms as well. But each individual derivative that we look at does rely on one of these properties. So those are the inverse properties for the natural log and the exponential base e. Hopefully you remember those. 2 is just the actual definition. So that's just the definition of our natural logarithm. When you say y equals the natural log of x, what that means is e to what power gives me x. E to the y power gives me x. The property number 3, if you'll notice, is also based on the properties of inverses. If I take the natural log of e to some power, then that will equal that power itself. So I guess that's for this property here. Yeah.
That's simply inverse relationship between e and natural log. Kind of looking at it both ways. If I raise e to the natural log of something, I also get that something. So those are just the inverse properties of each other. And then 3 gives us a way to rewrite any exponential. So like any exponential whose b is larger than 0, we can rewrite it as e to the x ln b. I'm going to look at it as b to the x equals e to the x ln b. Like I said, all 3 of those are utilized in this section to justify the derivatives of exponentials and logarithms. So the first thing we're going to look at is the derivative of the natural log. So at this point you have the definition of the derivative that we could go through and say, all right, well, if I'm going to find the derivative of natural log, I need to say that it's the limit as h approaches 0, natural log of x plus h minus the natural log of x all over h. Compute that limit, right? Simplify the difference quotient. Or since we have other techniques at this point that we've developed, we can try to look at y equaling the natural log of y equals the natural log of x in a different way. We can say that if y is the natural log of x, what that means, so we'll just write this sort of double implication arrow. But what that means is e to the y is equal to x. Right, that's the definition of the natural logarithm. Although we don't know the derivative of the natural log of x, can we take the derivative of our e to the y equals to x? Yeah, we can take the derivative of e to the y equals to x using implicit differentiation. Implicit differentiation. Because whatever the derivative of e to the y equals to x is, since it's the same as the natural log of x, we'll sort of bypass working with the derivative directly. Okay, what's the derivative of e to the y?
1 to the 1.
Yeah. Y prime times e to the y equals to the derivative of x, which is 1. And then we solve for y prime, right? We're trying to find the derivative. We're solving for y prime. Y prime is 1 over e to the y. We don't want it like that, right? We don't want to say our derivative is 1 over e to the y, because we know e to the y is the same thing as not the natural log of x, but e to the y is x, right? That was our reformulation of the statement y equals natural log of x. So we just have y prime being 1 over x. So when we're looking at the natural log function, ln of x, its derivative is just 1 over that argument. You just take 1 over the argument, which is whatever x is. But what we're looking at here is merely how to take the derivative of the natural log function itself. There's no chain rule applied to this. So we know that if we apply another function of x, if it's like x squared, or if it's the natural log of sine of x, right? The only thing in addition that we have to do is multiply by the derivative of the inner function, right? So what we're looking at is just the derivative of the outer function when the outer function is the natural logarithm. If we wanted a more generic statement, we would have to say the natural log of some function of x. If y is the natural log of some function of x, then y prime is 1 over that function times the derivative of that function, or f prime over f. So what we have in blue is more worthwhile to remember than just the 1 over x part. Again, we're applying that rule here when we say 1 over x times the derivative of x. That derivative of x we're not writing, but it's still sitting right here. So if your outer function is natural logarithm, to take the derivative of that, you do 1 over the argument, and then you multiply by the derivative of the argument. So we'll look at a few examples. So let's just say find y prime. So let's say we had the function y is the natural log of x squared. The derivative rule says that we've got natural log of some function. We're going to take 1 over the argument, and then we have to multiply by the derivative of the argument. So we have derivative of x squared is 2x over the x squared. We simplify that as just 2 over x. That's the derivative of natural log of x squared. So natural log is the function. You take 1 over the argument, then you multiply it by the derivative of the argument. But notice the properties of logarithms is something you should know. You should, if you forgot it, you need to look over those. Because if we say y is the natural log of x squared, maybe some of you remember that if we take the log of something that's raised to a power, what can we really do with that power there? So you might have seen the rule like this. If you have the log of something raised to a power, does that seem familiar at all? I'm not sure how your textbooks actually state it. So you all need to look over the properties of logarithms. The log of something raised to a power, the power can come out front and multiply the logarithm. So that 2 can really come out front and multiply the natural log, and we'll just have the natural log of x. That 2 comes out front. So before we even took the derivative of the natural log of x squared, we could have rewritten in terms of properties of logarithms and say that, well, that's equivalent to just 2 times the natural log of x. And we know the derivative of the natural log of x is just 1 over x. So it's 2 times 1 over x, which gives us this same thing.
how about if y is the natural log of sine x?
Again, all of these are chain rules at this point. The biggest indication that you have a chain rule is that we will only have this one occurrence of x, right? It's not ln of x times sine of x. That would be a product rule. Okay, does everybody see that? This is a product rule. That's not what we have. So it's 1 over the argument, 1 over sine x, times the derivative of sine x. So we have cosine x, derivative of sine, over the original argument here. Cosine over sine, which we could write, if we wanted to, we could write that as cotangent. I think either one of those is okay. Does anyone have any questions? Example 3. So the function is the natural log of e to the 2x. So what do we do here? Y prime, define y prime.
Where did the 2x come directly out front from the ln?
Yeah, so before we took the derivative, we could say, well, isn't the natural log of e raised to the power just the power itself? So the function is actually just equivalent to 2x. What's the derivative of 2x? Okay, so that's the derivative of the natural log of e to the 2x. If we wanted to look at it, you know, a long way, I guess, we would say, well, the outer function is the natural log, so we have the derivative 1 over the argument times the derivative of the argument. Just to see that if you miss a property of logarithms, it's not going to be a detriment. It is easier once you recognize them. But a process that we look at later on in this section, you do need to know the properties of logarithms for sure. So the derivative of e to the 2x is what?
2x, and the 2x isn't it?
Say that again. 2 times.
2x.
No.
Just 2e to the 2x.
2e to the 2x. Remember, e to the power times the derivative of the power. The derivative of 2x is 2. All over e to the 2x. Okay. Once we simplify that, we see that it's equal to 2. Does anyone have questions on that?
I have a question. What would you do to find the derivative of y equals ln
So the derivative of y equals to the ln of e, like that?
Yeah, well, y prime.
For this function here? just making sure I understand you correctly like that. Yeah, so what would the derivative of the natural log of e be?
0.
0. How do we know it's 0?
Natural log of e is 1.
Natural log of e is just 1, right? Because we can envision that as e to the first power. Natural log and e kind of cancel each other out. Or the other way just to think about that is that this is a constant. There is no x involved, right? That's like asking what's the derivative, what's the derivative of e to the 4 pi? 0, because it's a constant, right? There is no x involved. Once we have an x involved, then it is a function of x. So like if I had, what's the derivative of e to the 4 pi times x, that's no longer a constant. Okay, so derivative of ln of e is 0. Yeah.
I have a question. Well, it's about implicit, but I'm not sure we're gonna learn that here. What if we add like the z value? We would do that, right?
So what do you mean, like if we had the derivative of e to the xz?
Yeah, it's like for the third dimension.
Yeah.
That's
So like that, again, the z is a constant with respect to x. Even if z is a variable, it's not going to vary directly with x. So like that's a Calc 3 thing.
Oh.
So when you start taking derivatives in 3 dimensions, you have partial derivatives. You have the derivatives in the x direction, the y direction, and the z direction. And you just hold the other variables constant. So the same idea does show up in Calc 3.
Okay.
Like what's the derivative of this with respect to x? Since there's no x involved, it's a constant. What's the derivative of e to the xz with respect to x? Well, we don't know what z is. It's just a constant though. We're just finding the derivative with respect to that variable. So z is a constant in that situation. But that's, a couple of years from now. Maybe a year or so. Okay, how about if y were the, let's do the natural log of e to the 2x minus e to the 4x. So there is no property of logarithms when you have the log of the sum or a difference. There is no property for those. So you just, this function you have to leave it as it is. You can't simplify that at all. Which again is another reason why we should be familiar with the properties of logarithms. So this time we take the derivative. The outer function is the natural log. The inner function is the e to the 2x minus e to the 4x. So the derivative, 1 over the argument and then we multiply that by the derivative of the argument. What is the derivative of e to the 2x minus e to the 4x? Yeah. 4e to the 4x. 2e to the 2x minus 4e to the 4x. Derivative of our argument over the argument. I mean, we could factor out an e to the 2x up top. We can factor out an e to the 2x on the bottom, but you know, for now, we're just going to get used to explicitly following the format, derivative of the argument over the argument. Does anyone have any questions on that? Okay. We'll do one more. So, you know, just adding more functions just makes the combination of functions that we can take the derivative of even more complicated. So, again, it really boils down to first, like, do you recognize what kind of function it is? Because then that's going to tell you what kind of rule you're going to use. So let's say we had the natural log of the natural log of x. What rule do we use there? Chain rule, do you all agree? Because we're taking the natural log of something. There's our x. We're taking the natural log of x right there. So we have the derivative of the natural log as the outer function is 1 over the argument, which again is the natural log of x. So 1 over the argument times the derivative of the argument. So what is the derivative of ln x? 1 over x. So we have 1 over that ln of x. That ln of x is this ln of x right here, times the derivative of ln of x, which is 1 over x. So we just have 1 over x times the natural log of x. So hopefully with those examples, you can kind of start to see the pattern involved when we take the derivative. Does anyone have questions on that? So then we'll move on to the next function. We're going to look at the derivative of y equals b to dx. Remember, b is, here b is larger than 0, not 1. So it's a real number that's larger than 0, but not 1. So we kind of do a similar thing. We don't know the derivative of b to the x. We could find the limit or compute the limit as h approaches 0 on the difference quotient. But we could also rewrite y equals b to the x in terms of something we already know how to take the derivative of. So this justification of this derivative is going to come from this third property right here. So for a real number x and b to the x is going to be rewritten as e to the x times the natural log of b. So this is based on the inverse property of e and ln and properties of logarithms. Because notice up here in this power, just the power itself, when it has the natural log of b raised to the x power, the log of something raised to a power, that power can come out front and just multiply the logarithm. So that's how come the power ln of b to the x is turning into x ln b. So b to the x is e to the x ln b. So instead of looking at it as b to the x, we're going to look at it as e to the x ln b. It's the same thing. Because I don't know how to take the derivative of b to the x just yet, but I know how to take the derivative of e to a power. So what is the derivative of y? The derivative of e to some functional power is e to the power times what? The derivative of the power. Yeah, so the derivative of our power. X times ln b. So we just need to compute the derivative of x ln b. Oh, the derivative of x ln of b equal to 1 over b. What do y'all think? So let's look at it like this. Kind of just pause on that for a moment. What if I told you to take the derivative of x times the natural log of 3? What would the derivative of that be?
X.
No.
1/3.
Okay, put a pin in that. What's the derivative of x times 5? Okay. What's the derivative? Let me rewrite that. What's the derivative of 5 times x? 5, yeah? What's the derivative then of this? ln 3 times x. ln 3, right? It's a constant. That's a constant. Constant times x. The constant comes out. We just take the derivative of x. 1 times ln 3 is ln 3. So that derivative is just the ln of 3. Do you all agree? Okay, so what's the derivative of x ln b? ln of b, right? ln b is a real number that's greater than 0 and not 1. So that's just a constant with respect to x. So we're going to pull this constant times the function of x. Constant gets pulled out times 1. So like you wouldn't say that it's like the derivative of this right here is not 1 over 3 because it's not a function of x. The derivative of the natural log of x is 1 over x. But the derivative of the natural log of a number is 0. It's still a constant. In this context, though, it's the constant times a function of x. Okay, so are there any questions about that? It's a bit weird at first, but it's ln of b is still a constant, like 5 or 12 or negative 36. Okay, so we have then the derivative of this. It's e to the x ln b power times the derivative of x ln b, which we said was ln b. And what do we know e to the x ln b actually is? It's the same thing as b to the x. So here's our derivative. That's b to the x times ln b. I'm going to erase this stuff here. So in other words, when y is b to the x, the derivative of b to the x is b to the x times the natural log of the base. And again, remember that this is only the derivative of your outer function when your outer function is b, like 2 to the power, 5 to a power, whatever. The more general rule, if y is b to some function of x, then we have y prime is b to that function times, what would we need to do here? That's not present here. At least that we're not seeing here is this step. B to the x, natural log of b, times the derivative of the power. Again, it's kind of like implicit differentiation. When you take the derivative of it, with y, you just tack on a y prime. It's like the chain rule here. How do we take the derivative of b to any function of x, as we normally would here, but then we just multiply it by an f prime. That's the chain rule. And for instance, if we looked at this, if we looked at applying this rule to e to the x, and we just have to look at this formula here where b is equal to e, right? B to the x, now we're looking at a specific b, which is e. So it says in order to find y prime, this is more generic than the e to the x rule, because that just applies to that specific exponential. This rule applies to any exponential. So we say the y prime according to this rule is the exponential itself times the natural log of the base times the derivative of the power. So just go ahead and write all of that out, because this is what our rule tells us to do. Exponential itself times the natural log of the base times the derivative of the power. And of course we see that both of these things here, ln of e and the derivative of x, are both 1. So y prime is just e to the x. But again, this rule here is for any exponential. Okay, sorry we went over a little bit. We'll pause there and take a break. Well, does anyone have any questions on this before we take a break? All right, so like I said, hopefully you have some sort of system going to remember these derivatives. Like we're getting through, we're essentially getting 3 more here, but with 2 of these derivatives, you have the derivative for any exponential function, and one we see later, you'll have the derivative for any logarithmic function. So you could throw out the derivative of e to a power, and you could throw out the derivative of the natural log of a power, and remember this rule and the one we look at next. That way, instead of having 4 derivative rules to remember, you only have 2. But anyways, you're getting a lot more derivatives here, so just gotta make sure you're keeping up with this stuff. All right, well. Okay, just 1 or 2 more examples here. Like if we were asked to take the derivative of 4 to the x, we would say the derivative is 4 to the x times the natural log of 4. And these are, these types are the most basic ones. The derivative of 1.7 to the power of x would be 1.7 to the power of x.
times the natural log of 1.7. So in any other instance, if it's not an x, then we're going to be using that blue formula where we're just multiplying in addition to this stuff, the derivative of the power. So are there any questions on what we've done there? Okay, so then we'll look at some ones that are a little bit more involved. So again, our instructions are just to find y prime. Y is equal to 4 to the negative x. What would y prime be for the derivative? So we go back. We're looking at this one here. This time our function is just negative x. So we have the derivative is 4 to the negative x times the natural log of the base
Times the negative 1.
times the negative 1 times the derivative of negative x. So 4 to the negative x, ln 4 times negative 1. And so typically you'll see that as negative of 4 to the negative x, ln 4. But the 4 is still the only thing being raised to the power of negative x. That negative 1 is just out here multiplying this exponential. If they were both meant to be raised to the negative x, you would see that negative 4 in parentheses. But of course, the interpretation is the same with our negative exponents. If we have 4 to the negative x, that's really 1 over 4 to the positive x. Second function, y is equal to, we'll do 250 times 1.045 to the x. So I don't know, you might see it like this. You might see just the exponential, or the base rather, in parentheses. So a couple ways that this could be written. So this time we have a constant 250 times the function of x, 1.045 to the x. So when we take the derivative here, that 250 is pulled out front of the derivative. So it's really 250 times the derivative of our exponential. Or 250 times, what's the derivative of 1.045 to the x?
.045 to the x times ln 1.045.
Yeah. 3.045 to the x times the natural log of the base. Or b to the x times natural log of b. Any questions on that? Example 3, y is the natural log of 10 to the x. So how are we going to take the derivative here? We're going to say the derivative is what?
Wouldn't it be 1 over 10x times the derivative of 10x?
Yeah, 10 to the x. So it's our function, our outer function is natural log, so we're taking the natural log of 10 to the x. So the derivative of the natural log of a function is 1 over the argument times the derivative of the argument. And the derivative of 10 to the power of x is going to be what? To the power of x, that's our b to the x. The derivative of b to the x is b to the x times the natural log of b. And then all of that is times 1 over 10 to the x power. So we just get the ln of 10. I think you can see that a little bit more immediate if we rewrite. We've got the log of something raised to a power. That's just x times the natural log of that thing. The power comes out front and multiplies the logarithm. Here we are again. What's the derivative of x times the natural log of 10? It's natural log of 10.
Or the 10x times 10, you're also times the automatic x, right?
Yes, right. What we're not seeing there is when we say we're computing this derivative, it's 10 to the x natural log of the base, b to the x ln b times the derivative of the power. But the derivative of the power here is 1. So yeah, if you can remember that, that's always the rule. Any other questions about this? I mean, we're just adding a few more functions on top of what we already have. You know, it can get really confusing because just adding more combinations of the types of functions we're able to take the derivative of. What if y were the what if y were 10 to the natural log of x power? So we're
we're still looking at this function. The overall structure of y is some number to a power of x. So this is still of this form, b to the power of a function of x. So that's how we're going to take the derivative of it. We're going to say the derivative of y is 10 to the ln of x power times the natural log of the base times the derivative of the power. Does that make sense? So then we just have 10 to the natural log of x times the natural log of 10. And then derivative of the natural log of x is 1 over x. Any questions? Maybe we'll do one more. Well, y is, let's do 6 to the negative x times sine x. We have the product of two functions of x. We're going to use the power rule. Have the first times the derivative of the second plus the second times the derivative of the first.
Thank you.
So we've got our negative, sorry, 6 to the negative x here times the derivative of sine plus sine times the derivative of 6 to the negative x. And so the derivative of 6 to the negative x would be
Negative 6 to the power of negative x times ln 6.
all right. Do y'all agree? We get 6 to the negative x times ln 6 times the derivative of negative x, which is the negative out front. Okay, so there's our derivative. Just know again that this is the sine of x times that quantity.
Would you want us to simplify it on the test or just something like that?
On the exam, something like that is fine. Most of these longer ones on our first exam, I'm not going to have you simplify because there's a couple of routes people can take to simplify. And all I'm really interested in on this exam is being able to apply the derivative rules correctly. Being able to simplify is something you should be able to do because once we hit chapter 4, then we're looking at stuff like this. So I don't know if it's currently, but this used to be a question in chapter 4. It says, where does 6 to the negative x sine x, where does that function have horizontal tangents? So you have to find the derivative, and then you have to set the derivative equal to 0, which involves solving this equation for x. Which again, it's primarily based on factoring out the greatest common factor. You have two things multiplying, giving you 0. But yeah, on the exam that's upcoming, I wouldn't have you simplify that. Like if you stopped here, then that's fine. That's all I'm really looking for.
So one thing I've noticed too when doing a lot of the homeworks is that, for instance, the -6 raised to -x ln6, would that be the constant with the sign of x?
The constant is just ln6.
Alright, because I've noticed on a lot of it that they'll put that in front of the sign x.
Yeah.
And with, I guess it's kind of an anal about that. Are we gonna have to do the same thing on the test, where make sure to have the constant in front of the trig function or the derivative of the trig function as well?
No, I don't care about that.
No? Okay.
I think, typically, like I said, the way with an earlier example, the way you would see this written out is like this. Just so it's not, and that's another reason or another instance where parentheses can help. Like if we just know that this is sine times all of that, I don't think there's any reason to have to put the exponential and the ln of 6 out in front. It's just to kind of avoid that ambiguity of, well, is it the sine of x times all of this stuff, or is it just the sine of x times this? You know what I mean? Does that make sense? If you just write it like that, it's just kind of confusing as to what's really going on, right? Is it the sine of x minus 6 to the -x? You know what I mean? So that's why they put this out front. So you can clearly see that it's this thing times this thing times this thing. It's not sine of x minus this or whatever. And I think that's sufficient as well. Like, that's -1 times that. So, but generally it's written like this instead, just to avoid unnecessary use of parentheses or confusion. But if my math lab counts you off for writing this instead of writing this, then just email me if you don't want to redo that, because I think that's really nitpicky. All right, any other questions on that? Well, then we'll move on to our final derivative. The derivative of our logarithms. Just so that we have inverses here, the b is still greater than 0, not equal to 1. It's a real number greater than 0, not 1. So this rule and rule number 2, again, they sort of eliminate the necessity for you to have to remember individually the derivatives of e and ln. We could just remember these last two rules because they take care of all exponentials and all logarithms. In order to look at this in a way that, or to rewrite this as something we already know how to take the derivative of, we're going to say that y is the natural log of, y is the log base b of x if and only if. So this means, again, this equation is equivalent to this equation. Just like we handled, or how we handled the logarithm. And then we're going to take the derivative of b to the y equals x implicitly. Implicit differentiation. Again, the derivative of b to the y is b to the y times y prime equals the derivative of x, which is 1. Solving for y prime, we have y prime equals 1 over b to the y. Oops. B to the y equals x. Let me see that. Why does that look weird? Okay, so that's part of it. Does anybody see what we missed?
Well, can we say that b to the y is like e to the y ln b?
Yeah. So we actually messed up on our derivative there. Exponential b to the y times y prime times,
The derivative of the power. Alright, so.
derivative of the power is right here. So we have the exponential times the
and we missed
derivative of the
log-
power.
We missed the logarithm.
We missed the natural log of the base
Yeah.
part. So solving for y prime, we should have 1 over b to the y ln b. All right. But b to the y was equal to x, so it's 1 over x ln b as the derivative of our logarithms. So that's how we take the derivative of the outer function when the outer function's a logarithm. And again, we can, look at, does this hold if y is the natural log of x? In other words, the log base e of x. Says to find the derivative, we do 1 over the argument times the natural log of the base. So 1 over the argument x times the natural log of the base e. 1 over x ln e is just 1 over x. Well, the derivative of the natural log of x is 1 over x. So the more generic one we want to remember is we've got the derivative of the outer function. Chain rule said we would need to multiply all of that by the derivative of the inner. So the only addition that we're going to make, I guess I already did that, but if y is the log base b of a function of x, the derivative is just, it's still 1 over the argument. So 1 over f of x, 1 over the argument, times the natural log of the base. And then the chain rule says we've got to multiply that by the derivative of the inner function. So we're just going to put that up here. So that's true for any logarithm. We saw that it was true for the log base e or natural log. So if you don't want to remember these generic ones, then just remember that they're all just a chain rule. You've got to multiply in addition to applying this rule right here. You've always got to multiply by the derivative of the thing on the inside of the chain rule. So for example, let's say y is equal to the log base 3 of x. The derivative then would be 1 over x, 1 over the argument, times the natural log of the base. Remember with these logarithms, log base b of something, you can use a change of base formula. So we could say if we use the change of base formula on the log base 3 of x, we could write it as ln of x over ln of 3. And then we could use the quotient rule here, where we say the bottom times the derivative of the top. Minus the top, ln of x times the derivative of the bottom. That's all going to be 0, right? Because it's ln of x times the derivative of the bottom, which is 0. All over the bottom squared. And we see one of these ln of 3's cancel out, so you have 1 over x on top, and you have one of these on bottom. So that just goes into the bottom with x. So that's the same thing as that. So we could have also like proved or justified we could have justified this rule by using the change of base and then applying the quotient rule to that. But we just went the implicit differentiation route. So that's the thing with logarithms, they have all these funky properties associated with them that you need to be familiar with, because now they're showing back up. Okay, so those are some basic ones. We'll look at a few more examples. Okay, so find y prime for y equals to the log base 2 of 3x. So this time the inner function is 3x. The derivative is 1 over the argument times the natural log of the base times the derivative of the argument. So that's how we find the derivative of any logarithm. That's always the formula. 1 over the argument ln of base times the derivative of the argument. So we have 3 over 3x ln 2. The 3's divide out. We have 1 over x ln 2. So like a simplification like that, you should do that. I mean, that's like a very, very trivial thing to do. When we say don't simplify in the exam, we mean don't factor out greatest common factors, combine like terms, factor other things out, simplify. Negative over negative should be written as a positive. You know, those kinds of things should be simplified. Does anyone remember the property for the log of a product? Like if you have the log of 3 times x, how that could be written? So the log of a product is the log of factor 1 plus the log of factor 2. So then we could say, well, instead of taking the derivative of log base 2 of 3x, I can take the derivative of the log base 2 of 3 plus the derivative of the log base 2 of x. What's the derivative of the log base 2 of 3? 0. Do y'all agree? Log base 2 of 3 is a constant. Remember, that's just 2 to what power equals 3 is what that number is. Derivative of the log base 2 of x. There's no chain rule here. We can just say it's 1 over the argument times the natural log of the base. 1 over x ln 2 is what we have here. sorry. We could also do implicit differentiation here. So, I'm not really trying to overwhelm you, but I think it's important to see that multiple things that we've talked about are still valid. It's just how do you want to look at it and which one do you want to apply? So if y is the log base 2 of 3x, then rewriting that in terms of its definition, that equation is equivalent to saying 2 to the y equals 3x. And then we could do this implicitly. In fact, that's how we got the formula for the derivative of the logarithm, was we rewrote it, and then we used implicit differentiation. So we can do implicit with this. Let's say the derivative of 2 to the y is 2 to the y prime ln 2 equals the derivative of 3 times x, which is 3. And solve for y prime. So 3 over 2 to the y ln 2. Remembering that 2 to the y was 3x. And the same result. So there's multiple ways to look at these. I guess you really don't have to think of it all three ways, but I think the more connections you have, the better off you're going to be. Okay. Any questions? Yeah. So that's just the chain rule, because we have the derivative. So this is really like we're taking the derivative of 2 times, or 2 to a function of x power, right? In this case, we know explicitly what y is, but y is this function of x. So we have the derivative. This is like now b to the f of x. And so the derivative of that is this to that power times the natural log of the base times the derivative of the power. So there's the y prime. I should make that a little bit more. Looks like a 1. Any other questions? All right, so other types of functions that we end up looking at, I guess that was just one example. Other types of functions that we do eventually start looking at, sort of a combination of like powers and exponentials. So we'll say the instructions are still find y prime for y equals x to the power of x. So when you see functions like this, and generically they take the form f of x to the power of g of x, like, I don't know, sine of x to the natural log of x power, x to the tangent x, whatever. Those kinds of things. We do already have one method that allows us to take the derivative of these, but it's important to note that these kinds of functions are not exponential, and and they're not powered functions. They're sort of like both at the same time. So you definitely can't use just a power rule to take the derivative, and you definitely cannot use just an exponential rule to take its derivative. One way we can take the derivative is based on, what was that? Based on the third property that was mentioned on the first page, where it said that if we have some number raised to the x, then we can write that as e to the x ln b. So one way we can handle this is to rewrite y in terms of this property. We can say that's e to the natural log of the function x to the x, which then the power comes out front. So that's e to the x ln x. Which now, if we look at it that way, it doesn't seem that terrible, because now we're just having to take the derivative of e to a function power. So if we say that y prime, the derivative of e to any power, a functional power, is still e to that power times the derivative of the power. So we can totally compute the derivative of x to the x by rewriting it as e to that power first. We've got a chain rule, and then out of that chain rule comes a product rule. So, we talk more about these later. I'm not going to finish that at this point, but it is noteworthy that you can take the derivative of these types of functions by rewriting them. We do see these functions more as we progress. So to take the derivative of y equals to some function to another functional power, we first rewrite y as e to the g of x times the natural log of f of x. And use the chain rule. So like a super common f of x to the g of x type of function that you might have seen is 1 plus 1 over x to the power of x. So you might have seen that defining the number e as x approaches infinity. Have y'all seen that? Okay. Some algebra textbooks will mention that. So like that's a really common function of the form function to another function's power. But you kind of saw that when you looked at interest. P is equal to a times 1 plus r over n to the nt. Do y'all remember that formula? And then when they said, well, when you compound it continuously, you have, oh sorry, I have the a's and the p's wrong, I think. Whatever, principal, future values over here, initial deposits here. So I think they call them A and P. But anyways, if you saw the function where it's a equals to p times e to the power of rt, do you remember that? And it said, well, it's compounded continuously. Compounding continuously just means the number of compounding periods approach infinity. So we'll look at this later when it comes up. But the idea is that this 1 plus r over n to the power of nt gets transformed into e to the power of rt, sort of by way of this definition: as x approaches infinity, that's equal to e. We have this n here turning into this r, but those are just like minor constants to look at. But anyhow, maybe offhandedly you've dealt with that. It's just never been. You just sort of were never told why that happened to be the way it is. But with this type of thing and with our limits, we can then talk about why this is equal to this. But anyhow, those do show back up. Does anyone have any questions at this point? These are the main rules that we get in this section, but also we get another differentiation technique, kind of like implicit differentiation. So that technique is called logarithmic differentiation. And before we meet next class on Thursday, please look over properties of logarithms, because we're going to utilize them when we go through this process. Okay. All right. I'm just going to write out what we're doing next, but we're done.